Hello everyone, my name is Nilakshi Mate. In previous lecture, we saw a basic concept definition shortly. Now we see one by one in detail. Now start today's lecture with the definition of the state. So what is meant by state? Consider a system not undergoing any change, and at this point all the properties can be measured and gives a set of properties that is known as the state. So what is meant by the property and the change of the property? First we have to know about these properties. So definition of the property is any characteristic of the system by which state of the system can be identified is called as a property of the system. So which are the properties? For example, volume, pressure, temperature, density, etc. So there are two types of main properties. These are extensive property and intensive properties. So student, you can understand what is meant by property of the system. Any characteristic of the system by which state of the system can be identified is called as the property of system. So in classic thermodynamics, the substance is assumed to be continuum, homogeneous matter with no microscopic holes. This assumption holds as long as the volumes and the length scales are large with respect to the intermolecular spacing. So, for measuring those parameters, the properties are divided into two types: extensive properties and intensive properties. Now we can see the what is meant by extensive properties. The properties that are dependent of the size or extent of the system, that is mass. Means in this property we are addition of two properties or a same properties at the different level or the state. For example, x is a some kind of property which is measured at the point A and point B. So this is the additive function. In short, the x properties which are dependent on the mass and the size of the system are called extensive property. So extensive property is dependent and it is a additive function. As shown in the PPT, x is a property at A and B level. So the function gets the value xa, means property at a point plus property at a B point. Now we can see the intensive property. The intensive property define the properties that are independent of the size or mass of the system. In simple language, the properties which are independent on the mass and the size of the system are called intensive property. Means this function is not additive type. Means if property x at A and B point is not equal, means property at A plus property at B point is not equal to the cumulative function x in bracket A plus B is not equal. So from these two properties we get the specific properties which define as a extensive properties expressed per unit mass to make them intensive properties. So which are the properties are belong to the extensive property and the intensive property? In extensive property we get the volume, mass, energy, enthalpy and the entropy. And in intensive property we get the pressures, temperatures, specific volumes and density. So the measurable properties are, we see, pressure, volume, temperature, mass. These are the important measurable quantities. In these quantities, pressure and temperature are easily measured. So these are the intensive properties. But note that they are not always independent of one another. Okay, and the volume and the mass are easily measured extensive properties. Now we can see these properties one by one. First we can see the pressure. So what is meant by pressure? Pressure is a force applied over a unit area. Once again I tell you, the pressure is a force applied over a unit area. Means the formula is force divided by area. In SI unit, means in international systems, the unit for pressure is the force of 1 Newton acting on a square meter area, which is called as a Pascal. That is 1 Pascal is equal to 1 Newton per meter square. At this unit is rather small for practical use. Engineers measure pressure in a kilopascal and megapascal. We know that 1 kilopascal is equal to 1000 pascals, means 1 kPa, and 1 megapascal is equal to 10 lakh pascals. 10 lakh pascals is equal to 1 MPa. Other units for pressures not included in the SI units but commonly used are bar and standard atmosphere. 1 bar is equal to 105 pascals, that is 100 kPa, means 100 kilopascal, and 1 standard atmosphere is converted and the value is 1,01,325 pascals, which is somewhat larger than a bar unit. Now we know about these pressures and what is the bar pressure, what is the atmospheric pressures, and how it can be calculated. So first we know that pressure is a force acting per unit area. Students, you get my point? Okay, so we take one example here. The atmosphere surrounding the earth exert a pressure on its surface equivalent to the weight of air over a unit area of the earth surface. The pressure of the atmosphere is recorded by a barometer. By which instrument we can recorded the pressure of the atmosphere? Is barometer. The height of the mercury column also varies with the altitude above or below sea level. As shown in the figure, we divided the pressure into 3 types: absolute pressure, vacuum pressure, gauge pressure, and absolute atmospheric pressure. At sea level, 760 mm of mercury column at 0 degree centigrade is taken as a standard barometric pressure. This is also known as the atmospheric pressure. To express this physical atmosphere in kilogram per square centimeter, we must first determine the weight of the column of mercury with a cross section of 1 square centimeter and a height of 760 mm. In this, we consider the density of mercury per cubic meter at 0 degree centigrade. Hence, the standard height of 760 mm at 0 degree centigrade of mercury column, it corresponds to a pressure. So 750 mm of Hg is equal to 100 kilopascal is equal to 1 bar. Okay, so now we can see about the vacuum. Vacuum may be defined as the absence of a pressure. Quite often, the pressure of the confined fluid is less than that of the surrounding atmosphere, but vacuum may be defined as the absence of the pressure. The confined fluid is then said to be under a partial vacuum. In such cases, the instrument used to measure the pressure is vacuum gauge. To measure a pressure in the vacuum, the gauge used is vacuum gauge. It records the difference between the surrounding atmospheric pressure and that within the vessel in millimeters of mercury. A vessel having no pressure within it is said to have a perfect vacuum. Means when the vessel having a no pressure, at that time there is a perfect vacuum condition. So how we can get the actual value of the pressure? In practice, pressure of a fluid is measured by means of instrument known as the gauges. Means any kind of pressure of the fluid we can measure with the help of gauges. The gauges which measure the pressure greater than the atmospheric pressure are called as a pressure gauges. Once again I tell you, gauges with measures pressure greater than the atmospheric pressure. Pressure greater than the atmospheric pressure is known as pressure gauges. A pressure gauge attached to a vessel indicate the difference between the pressure inside the vessel and the pressure of the atmosphere. So for that purpose we can use various types of gauges, but simply in regular practice Bourdon pressure gauge is used. So we take that example for easy understanding. The Bourdon pressure gauge. This pressure gauge is commonly used to measure the pressure of steam in a boiler. The reading of the pressure gauge is called as a gauge pressure, and the absolute pressure of the steam within the boiler is therefore equal to the observed gauge pressure plus the atmospheric pressure. As I said, the pressure gauges attached to the vessel indicates the difference between the pressure inside the vessel and the pressure of the atmosphere. So in our example we take example of steam boiler. In that the pressure gauge attached to the boiler and the readings which shown by the pressure gauge is called as a gauge pressure. In this gauge pressure, the absolute pressure of the steam within the boiler is equal to the observed gauge pressure plus the atmospheric pressure. Means the boiler pressure is equal to the gauge pressure plus atmospheric pressure. Then we get the absolute pressure in the of the steam in the boiler. Get my point? Now onwards, gauges measuring pressure less than atmospheric pressure are called vacuum gauges. As I earlier said that the vacuum means the absence of the pressure. So the gauges measuring pressure less than the atmospheric pressure are called vacuum gauges. The principle of working of pressure gauges is same. The pressure in the steam condenser is usually less than atmospheric pressure. We are taking an example of steam in the boiler, means the steam power plant. So we going forward the instrument used in that plant, so we get the all type of gauges which we are studying now. Again I said the principle of working of pressure gauges is the same. So the pressure in a steam condenser is usually less than atmospheric pressure. A vacuum gauge attached to the condenser measure the difference between the atmospheric pressure and the pressure inside the condenser. This difference is called vacuum and is expressed in a millimeters of mercury. What I say, a vacuum gauge attached to the condenser and measure the difference between the atmospheric pressure and the pressure inside the condenser, but in actual the pressure in the condenser is less than the atmospheric pressure. So the difference between atmospheric and the inside condenser pressure is get the value of vacuum and is expressed in the millimeters of mercury. So the absolute pressure within the condenser is equal to the atmospheric pressure minus the vacuum. Get my point? Now we can study about the diagram presented in the PPT. So for that purpose we assume a principle of working of U-tube manometer measuring pressure above the atmospheric pressure. So consider one limb of U-tube manometer is open to the atmosphere and the other end is connected to the vessel which having a pressure more than that of a atmospheric pressure. So suppose the manometer indicates a reading of H millimeter as a difference between the mercury level in the two limbs of a U-tube manometer. So at that time the pressure of the gas P is being balanced by the atmospheric pressure, which we are consider as a P ATM, means P atmosphere. That pressure due to the column of a mercury at height H. So the actual pressure we can find out by the addition of pressure due to atmosphere plus the height of the mercury in that column, and the pressure we get is the absolute pressure of the gas in the vessel or the pipeline is the sum of both reading. Once again I tell you, the absolute pressure of the gas in the vessel or a pipeline is the sum of atmospheric pressure and the manometer reading, means the height of the mercury and the difference between the mercury levels in the two limbs of the U-tube manometer. Okay, now going forward, second example with same condition, means we are using U-tube manometer for measuring pressure which having a pressure less than atmospheric pressure. Earlier I said that the lesser the pressure than the atmospheric pressure means there is a vacuum. So the one limb of the U-tube is open to atmosphere and the other end is connected to the vessel having a pressure less than the atmosphere. So the absolute pressure we get by taking a difference between the pressure due to the atmosphere and the manometer reading. So you can get the absolute pressure. Get my point? So the practically in thermodynamic analysis and calculations, absolute pressures we used. Now you can understand what is meant by pressure, which pressures are used in thermodynamics and how they can find out. We study with the help of U-tube manometer and the barometric pressure gauge. Now we can see the volume. Volume is also a very important property in the thermodynamic systems. So what is meant by volume? Volume of gas is defined as the space which the gas occupies and it is measured in cubic meters. Means the gas occupied the space, that whole space which get is known as volume, and the volume is measured in the cubic meters. A widely used unit of volume is the liter, which is 1000th part of the cubic meter. Means 1 liter is equal to 10 raised to minus 3 meter cube. So moving forward, the specific volume of a substance is its volume per unit mass. It is generally used in cubic meters per kilogram. What I say, the specific volume of a substance is its volume per unit mass. It generally stated in kilogram per cubic meter. It is generally in the cubic meters per kilogram. For example, 1 kilogram of air at 0 degree centigrade. We can take 1 kilogram of air at 0 degree centigrade and under a pressure of 101.325 kilopascal, which is 760 mm of Hg, and has a volume of 0.7734 cubic meter. So the specific volume of air under these conditions, we can get the 0.7734 meter cube per kg. Our definition already says that the specific volume of the substance is its volume per unit mass. It is generally measured in the unit of cubic meters per kilogram. So in our example, we take 1 kilogram of air at 0 degree centigrade, and the volume of any vessel is 0.7734 cubic meter. So the mass of the air is 1 kg and the volume of that vessel is 0.7734 cubic meter. So the specific volume of air we can get is 0.7734 meter cube per kg. One another important factor is the density. The density of a substance is its mass per unit volume. It generally stated in kilogram per cubic meter. So from this definition we can get the density and the specific volume. So it is clear that the density of any substance is a reciprocal of a specific volume and vice versa. So we can take the one example that 3 kilograms of dry hydrogen occupies 33 cubic meter. So what is the specific density of hydrogen? So specific volume is 33 divided by 3, means it is 11 meter cube per kg, as the definition says that volume per unit mass. So in this example we take 3 kilograms of dry hydrogen which occupies 33 cubic meter area. So the specific volume is cubic meter volume is 33 and the mass is 3 kg. So our specific volume is 11 meter cube per kg, and the definition of density says mass per unit volume, means the density and the specific volumes are reciprocal of each other. So we can get the density is 1 divided by specific volume. So our example is 3 kilogram of dry hydrogen occupy 33 cubic meter area. So we get the specific volume is 33 divided by 3 and get the value is 11 meter cube per kg. So density we get now by using formula 1 divided by specific volume, which is 1 divided by 11, and the answer comes is 0.09 kg per meter cube. Now you can understand the volume, the specific volume and the density terms and their correlation. Now moving forward, we see the next property is temperature. So what is meant by temperature? So first we understand the definition of the temperature. The temperature of a substance may be defined as a measure of hotness or degree of coldness of any body. Of any body. A body is said to be hot when it has a relatively higher temperature. It is said to be cold when it has a relatively low temperature. Means the body temperature when it's relatively high means we know that the body having a higher temperature, and when the body having a lower temperature or relatively low temperature, then we get that or we know that the body is now cold. So temperature is the measuring parameter to identify the degree of hotness or degree of coldness of a body. It is known fact of heat energy has a tendency to flow from the hot body to one that is a cooler body. It is another term that the heat energy has a tendency to flow from the hot body to one that is a cooler body. So thus the temperature determines which way the heat flow will take place. It is not a measure of quantity of energy possessed by a body, but it indicates the level of internal energy possessed by the body. So, ordinarily temperatures are measured by the instrument which is called as a thermometers, and very high temperatures are measured by the instrument known as the pyrometers. So small and precise changes of temperature can be measured by the resistance thermometer and the thermocouples. These are the instrument used for the temperatures with the various ranges. As I says that ordinary temperatures measured by the thermometer, very high temperatures measured by the pyrometers, and small and precise change in the temperature can be measured by the resistance thermometer and the thermocouple. So the unit to measure the temperature is centigrade. That centigrade scale in SI unit is now named after Mr. Celsius, which is the Swedish astronomer who invented this scale in 1953. Therefore, this scale is known as Celsius scale. So, normally engineers measure temperature by centigrade thermometer. Centigrade thermometer. So in that centigrade thermometer, the freezing point of water is marked as a 0 and the boiling point as a 100. So the freezing point and the boiling point of water at atmospheric pressure are called fixed point of the thermometer. Other temperatures are measured by the reference of these points. So the centigrade scale of temperature is constructed by dividing the thermometer stem between the fixed point in 100 equal parts or degrees. So centigrade scale may be extended above the boiling point and below the freezing points. So temperatures lower than 0 are denoted by negative signs. So for example, we take the minus 15 degree means it is a negative or lower than the freezing point, and the 15 centigrade degrees below these freezing points. And above temperatures we can get one example is 300 degree centigrade, which is more than the boiling point of the water. Okay, now we can see the next property is energy. Before moving forward, I want to tell you that the temperature can measured in the centigrade or in the Celsius scale, and the absolute temperature is the temperature measured above the point of absolute zero. So the absolute temperature are expressed by the capital letter T, and the absolute temperatures is expressed in the degree of Kelvin. So the Kelvin scale is denoted by the letter capital K, and the relationship between the Kelvin and the Celsius scale is temperature measured in Kelvin scale can be found out by the summation of temperature in centigrade scale plus 273. This is the formula to find out the temperature in the Kelvin scale. Now we go forward to know about the energy. So what is meant by energy? Energy may be defined as the capacity a body possesses for doing work. Once again I tell you what is meant by energy. Energy may be defined as the capacity of a body for possessing to doing work. Energy appears in many forms, that is mechanical again containing two type of energies, potential energy and kinetic energy. Then internal energy, electrical, chemical, nuclear, work, heat, etc. So energy cannot be seen and does not have a mass. So all forms of energy mainly can be classified as a stored energy and energy in transition. So energy residing in a system is called a stored energy. Now we can see with the help of one example. Energy found stored in many such forms such as mechanical, internal, electrical, as I earlier said to you. So mechanical energy is concerned with a system as a whole. It may be in the form of kinetic and a potential energy of a body as a whole, and internal energy is associated with the molecules of the system. So the system has ability to receive, to store and to emit the energy and undergo a thermodynamic processes that results as a change in properties of the system, and the change in stored energy of the system must derived completely from the energy which has transferred across the boundary, as earlier I said you in previous lecture. Since energy can neither be created nor be destroyed. Now we can see the energy in transition is the energy that is transferred to or from a system. So transient form of energy has a significance only while energy is being transferred. Means the transient energy is can be calculated when the energy is being transferred. So work and heat are forms of energy in transition which can only cross the boundaries of the system, which is already we are seen in previous lecture. So work and heat are not stored by the system, hence there is nothing like work of a body or heat of a body. So work and heat are not a properties or state parameter, they are not a state functions, they are only path functions. They exist only in transition or transfer of a energy. Now we can see the forms of energy. First we see the work. So what is meant by work? Work is a transient form of energy when a force acts upon a body, causing a body to move and to overcome continually a resistance. Work is said to be done. Once again I tell you, work is a transient form of energy when a force acts upon a body, causing the body to move or to overcome continually a resistance. At that time work is to be done. This work is equal to the force multiplied by the distance through which it acts. This time element, the time element is of no consideration. So the unit of work done is Newton meter, which is the product of unit force and the unit distance moved in the direction of the force. So the unit of work is also known as joule. So 1 joule is equal to 1 Newton meter and 1 kilojoule is equal to 1000 joules. Now we know about the heat. Now we get the information about the heat. So what is meant by heat? Heat is that form of energy which is transferred from one body to another body on account of temperature difference. So as we earlier said that the temperature have a property, or a temperature of a body is transferred from the hot body to the cold body. So that condition is appeared when we check for the heat property. So heat is that form of energy which is transferred from one body to another body. So it is a temperature difference is in account. So heat energy may be transferred in three ways: by conduction, by convection and radiation. In all three modes of heat transfer there must be temperature difference, and the direction of heat transfer is in the direction of decreasing temperature. It may be noted that conduction and convection require some definite medium, while radiation can occur in vacuum also. So we see these three terms one by one. So first we see what is mean by convection. Heat is transmitted from one place to another by fluid currents. As gases or liquids are heated by conduction through the wall of containing vessel, they tend to expand and rise, and their place is taken by the upper colder layers, while being heavier than the heated liquid or gas tend to flow downwards. In this way, the convection currents are set up and whole volume of gas or liquid is gradually heated to uniform temperature. Now we see the conduction. In conduction, the molecular activity at the hot end causes the molecules in an adjacent section to increase their molecular activity. Thus, the energy is carried along the entire length of the bar, and the temperature of the cold end rises. If the two ends of the bar are at same temperature, the molecules of the two ends have the same level of molecular activity. There is no tendency of energy to be transferred from one cross section to the next. So there is no heat transfer. This mode of heat transfer is called conduction. Now we see the information about the radiation. Radiant heat is in the form of temperature excited electromagnetic waves which passes from one body to another without much raising the temperature of the medium through which it passes. Substances which are transparent to light usually allow radiant heat to pass freely through them even when they are poor conductors of heat. This one reason why radiant heat is so important in boilers, since it will pass through a thin film of gas to the tube or plate, which offers considerable resistance to the passage of the heat. So in steam boiler, the heat from the surface of the burning coal in a furnace is transferred to the crown and sides of the furnace by radiation, and it passes through the furnace plate by conduction, and the water is heated by the help of convection. This is the perfect example. In that example we know about the conduction heat, convection heat and radiation heat. Now moving forward, we knowing about the potential energy. So what is meant by potential energy? Potential energy is the energy of a body due to its position or elevation relative to some datum plane. Therefore, the term potential energy exclusively used for gravitational energy. The potential energy of a substance is equal to the work that can be done by allowing a substance to fall from the given position to the surface of the earth or other datum plane. So the unit of potential energy is Newton meter, and the symbol to use to represent this energy is capital PE. If body of m kg mass is allowed to fall from an elevation L2 to an elevation L1, the change in potential energy we get. So we represent as a PE is equal to PE2 minus PE1, means potential energy at elevation level 2 to the potential energy at elevation level 1. So the formula for the potential energy is mgh. So in this condition we have to find out the actual potential energy in our mass of the body. So the formula becomes mg in bracket elevation level 2 minus elevation level 1. We get the actual potential energy in the body of m kg. Now we can see the information about the kinetic energy. The kinetic energy possessed by a body is due to its motion. The unit is capital K E and is also measured in Newton meter. For example, a body of mass m kg moving with the velocity v possesses a certain amount of kinetic energy with reference to the earth. So that energy can be found out by Ke is equal to mv square divided by 2. How we can get this formula? For example, water held behind a dam has a potential energy, and if released, the water in its flow has its potential energy change into kinetic energy, so that the energy could be utilized or work could be done equal to the energy possessed by the water. By permitting it to flow through the blades of the water wheel or a water turbine, a body of mass m kg with the velocity v possesses a certain amount of kinetic energy ke with reference to the earth. So that's why we get this formula is ke is equal to mv square divided by 2. Now moving forward, we see the information about the internal energy. So what is meant by internal energy? The internal energy is denoted by U, and it is a substance may be defined as the algebraic sum of internal kinetic energy and the internal potential energy of its molecules. The internal energy we get. Internal energy is an extensive property since it depends upon the mass of the system. The internal energy value of a substance in any event is measured above an arbitrary datum condition at which the substance or a medium is said to possess zero internal energy. Once again I tell you, the internal energy value of a substance in any event is measured above a arbitrary datum condition at which the substance or medium is said to be possesses zero internal energy. The value of internal energy is expressed in joules. So the change of internal energy when the substance passes from state 1 to state 2 can be expressed in general way, and it can be get by delta U is equal to energy possesses at state 2 minus energy possesses at state 1 means U1. U2 minus U1 is equal to delta U. And we take one example here. A change of mechanical potential energy of a body occurs when the elevation of the body relative to the earth of the datum is changed. The force acting in this case is the force of the gravity. Now, since there is a cohesive force between the molecules of the substance, there will be a change in the internal potential energy. If anything happens which increases or decreases the average distance between the molecules, it may be noted that the distance between the molecules can be more widely increased or decreased in a gas than in a liquid, say water. So during the formation of the steam, the molecules of water are separated against their attractive force, which is required a large amount of energy. So the energy used to overcome the attractive force is stored in a steam as a internal potential energy. Get my point? This is the information about the internal energy. Now we can see the last term is enthalpy. The other terms in use for enthalpy are total heat and heat content. It is said to that the term enthalpy is more convenient than the term heat content and total heat. So enthalpy is an energy term and it is defined as a capital H, and it is calculated by U plus P into V, where U is the internal energy, P is the absolute pressure and V is the volume. Since we cannot measure the absolute quantity of internal energy, it is impossible to measure the absolute enthalpy of a substance. What we wish to know in actual practice is the change in internal energy and change in enthalpy. Wherever the change of internal energy can be calculated and whenever the product PV is known for any two state of any fluid, so the change in enthalpy can be calculated. So today's lecture we are seeing about the information of properties and various type of properties in details. In next lecture we are moving and getting information about the state, path functions, path systems, processes and laws of thermodynamics. Thank you.